last time we assigned like 1 through 14 or something. Does that sound right?
Yeah.
Do we have any questions on any of those? I think it should have been relatively straightforward. Mariana? The answer for what? 12, absolutely. All right, let's grab that so everybody else that maybe doesn't have their stuff handy can look on. So it says find the component form for the vectors indicated below. Round your answer to the nearest hundredth. Where's my pen at? What's up? Sure. All right, so 12.
If we do 10 after that too.
Yeah, remind me though, because I'm probably at that point. I'm probably more than 2. I can't remember, but I will definitely do it. Okay, so if I go back and I look, what I want is the resolving vector to component form formula. So I'm just going to use this guy right here from last time. So the magnitude times cosine, comma, magnitude times sine. So we'll say u is going to be 4 times cosine, 2 root 2 times cosine of 5 pi over 12, comma, 2 root 2 sine 5 pi over 12. So far, so good. So what do you notice that looks funny about the angle measure that's given to me? Yeah, it's in radians. So before I go and start typing this into my calculator, I'm going to change it to radian mode. So I'll do that. Then I have 2 root 2 times cosine 5 pi over 12. And I'll press enter. So that's my value for the x component. And then I'll just steal that thing that I just typed in and just change the cosine to a sine. So that's the value for my y component. So 0.73, comma, 2.73. And that ought to do it for us. Mara, does that feel good? Okay. Tia, you said you wanted to do 11. Oops, that was V that I wrote. This is U. So 11, same idea. We're just going to have 4 times cosine 218, comma, 4 times sine 218. But what am I got to remember? This time my angles are in degrees, so I'm going to have to change my calculator mode back. Ugh. But that's no big deal. So I have 4 times cosine 218. So that's my x component. And then I'll just steal that same thing and just update the cosine to a sine. That's my y component. And I forgot. I couldn't remember it. 246. Tia, does that sound good to you? Feel okay? Again, for the most part, the problems here should have been not too bad, right? Like there's not a lot of work to do to get to our answers. These ones 7 through 10 are probably the most involved or the most difficult to the block of problems here that are given. This is yours, Josh, right? Look, I even remembered. So it says find the magnitude and the direction. Okay. So let's start with the magnitude. So I know the magnitude, if I'm in component form, is just the x component squared plus the y component squared, all square rooted. So that's 144 plus 25, that's 169. So that's just 13. Hi, Aaron.
I checked it.
Sounds good. Everybody, Josh, you feel okay there? Yep, the direction is the trickier part. So to do that, I'm going to start by drawing a picture. So I'm going to plot the point 12, negative 5. So that's like 12 over and 5 down. So that's my direction, right? In quadrant 4. So when I draw my angle phi or alpha, it's always going to be between the x-axis and the terminal side. So there's my alpha. So my theta should be 360 minus alpha. So that's, and alpha is always going to be tan inverse the absolute value of the y coordinate over the x coordinate. And there we go. That's all I need there. So 360 minus tan inverse. And I'm going to do the absolute value in my head rather than typing into my calculator. It's pretty easy to make 5 positive in my head. Don't struggle with that too bad. So I get 337. I guess it asked me to round to the 100th or something there, though, right? I guess I need some decimal points. 0.38. So there's my magnitude and direction. Kolb's. Sure. Is this all going so far so good? Josh, was that what you needed? Okay. I like all the questions we're getting this semester. It's like maybe we did the homework in advance of class. I like it. Okay. So it says, given that A, B, C, D are the coordinates, or are points whose coordinates are given, find the component form for the vector CA. So if I look at CA, C is the tail, and A is the head, right? I can tell that, Colby, because the C is under the tail of the arrow, and the A is under the head of the arrow. Are you good with that?
Yeah.
Okay. So if I do my head minus tail then, so I have head minus tail for X, and then head minus tail for Y. And then we're done. Does that feel okay? Okay. Again, it's one of these that like the directions sound like there's a lot to do, but if you can like sort through the vocabulary, what we're actually doing is pretty quick, pretty easy. We're just subtracting things. It's just knowing like which things to subtract from what does it mean when I hear that word. That's the hard part right now, is just kind of like getting through the vocabulary piece. Max?
And then for when we do direction problems, for the angle we choose is the like next line that it would cross is the angle that we put down. I said that weird. It like, so for this one you wouldn't do not 180 but the one between 180 and 360. You pick 360.
So
that's the next.
Yeah, so I mean like you could do like here and then plus this is alpha. The problem is that like calculating that isn't always going to be then just the absolute value of y over x. Like the way I've set it up, it's the same problem every single time, and you don't have to like, once you have it set up, it just like, you know, tan or alpha is always going to be tan inverse of y over x, or absolute value y over x. But like if you do it that way, it's the same every single time. But when you draw that alpha, it's always got to be between the x-axis and the terminal side.
And it's, yeah, it's Y over X.
Yes. So if you do it that way, it's the same all the time. You could do it the other way, but it's like things change. And it's like you got to really think about it a lot more. It's not wrong to try to do it that way, but I think it's harder to consistently get the right answers.
That's what I'm just trying to do, to write all the formulas down.
Yeah, totes. Last call on questions. I think we've taken a good spattering of them. Jack?
Can we do number 9?
9, sure. So 9 is 5, negative 12. So we'll start with the magnitude. And again, that's just going to be the x component squared plus the y component squared. So that's 25 plus 81, so that's 106. 5 and 10, okay, sure. So that's 125. Excuse me, thank you. Negative 10, yep. Still 125, but yes, that would have been disastrous when we got to direction. Thank you, Colby. And can we simplify that at all? That's 25 times 5. Yeah, sure. So that could be like 5 root 5. Or if it, I can't remember what the directions say. Find your, it doesn't say anything about how they wanted the magnitude. So decimal, or radical, reduced radical, any of those would be appropriate. The directions aren't specific about that. So now to do the direction, we'll plot negative 5, 10. So it's like down here. So that's my theta. My alpha, again, always between the x-axis and the terminal side. So that's my alpha. So theta is going to be 180 plus alpha. And alpha is always going to be tan inverse the absolute value of y over x. And now it's just calculator time. Jack, is that feeling okay?
Yeah.
Okay. And again, I'm going to skip doing the absolute value in my calculator because, dude, I can make stuff positive in my head and it's like a lot less buttons. So I get 243.43. So there's my magnitude and my direction. Yeah, Tia? Sure. Okay. So 6 is the vector DC. So the tail here is D. Oh, I didn't find the magnitude for this. I guess it asked for the magnitude. And the head is C. T, are you okay with how I came up with that?
Yeah.
Okay. We'll do the magnitude for this one. So again, it's always going to be head minus tail. So there's my component form, and I forgot to do the magnitude earlier. I guess the directions ask for that also. Oopsie-daisy. I forgot to do that last time. I did ask for the magnitude afterwards in the question, so I just went ahead and did it for this one. You would have had to do that for number 4 also, but it's just the square root of the x component squared plus the y component squared. So that would have been 25 plus 64, so square root 89. So those vertical bars, when they surround a vector, don't mean absolute value, they mean magnitude. So that's what that symbol means. If those vertical bars are around a number or a variable, then they mean absolute value. But if they're around a vector, they mean magnitude. And you can tell it's a vector because it wears the vector hat.
Yeah.
Does that do it for you?
Yeah.
Okay. All right, you guys ready? Oh, Matthew. 5? Sure. So that's this vector BC. So again, going to start by identifying the head and the tail. So the tail is B, and the head is C. So we have head minus tail, comma, head minus tail. So that's -7, comma, 13. And so my magnitude then is going to be -7 squared plus 13 squared. Yuck, 49 plus 169, that's 218, I think. And that probably doesn't reduce. That's 2 and 109, and 109 is, I don't know that that has a perfect square in there that I can see right away. It's not divisible by 2 or 3. Maybe it's like a 17 or something in there, but I don't know. I'm going to call that good enough. Matthew, does that do it for you?
That's good.
Okay. All right. We move on to section 2. So in section 1, we kind of learned what a vector was and the different ways to represent that vector and the different properties a vector can have, like ways to describe it, whether we want to describe it with a magnitude and direction or with a component form or as a set of 2 points, and then how to convert in between those different forms, right? That's essentially what we did in section 1. In section 2, we're going to talk about what we can do with those vectors. So we're going to talk about how we combine these vectors together, how we add them and subtract them, and we can multiply, and what are how does that work, and what do those operations look like? Everybody cool with that plan? Okay, so we're going to start by defining a special vector. And this vector is special because it's the only vector that has no direction. Ooh. It's called the 0 vector. So the 0 vector we denote with, that's that bold-faced 0 there, right? It's the same thing as that 0 wearing a vector hat. It's not the number 0, right? It's a vector 0. Its component form is 0, 0. It has magnitude of 0, and because of that the vector's terminal point is at 0, 0, and its initial point is at 0, 0, it's not actually like a ray at all, so it has no direction. It's the only vector that's allowed to have no direction. Very similar to the real numbers where 0 is the only number without a multiplicative inverse, because the reciprocal of 0, 1 over 0 is undefined. Same kind of idea. It's a special number in the same way that the 0 vector is a special vector. So if we want to add 2 vectors, we'll start with vector addition. So if we have the vector u, which has got the components u1 and u2, and the vector v with components v1 and v2, if we add them together, the sum, or often we'll use the term resultant vector. So sum and resultant in vector speak kind of mean the same thing. It's just going to be the sum of the x components plus the sum of the y components. That's all we're doing. So graphically, so if I have, say, this is my vector v in component form, and that's my vector u. If I wanted to add those two things together, what I'm essentially doing is I'm taking my vector v, and at the end of vector v, I'm putting my vector u. And the new vector that starts at v and ends at u is that vector u plus v. That's like our resultant vector. That's graphically what we're talking about when we add two vectors, is we're just placing the vectors head to tail. Does everybody feel okay with that idea? Should feel pretty straightforward. That should make sense just from looking at the formula. If I add their x's and add the y's, that's essentially taking, you know, the end of one vector, starting there, and putting the other vector at that end, right? Of course. All right. Our next vector operation is called scalar multiplication. It turns out that there is not multiplication between vectors, but what we can do is we can multiply a vector with a number. So when we say scalar, what we're talking about is just like a regular number, like 2 or -5 or 18. We can multiply a vector by a number, and the way we do that is we just multiply each component of the vector by that number. So what are we talking about graphically? Well, let's kind of show you. So let's say this is our vector u. My vector here is 2u, where it's essentially the same vector, it's just now like twice as long. Has the direction changed when I've done this scalar multiplication? No, right? That vector is still in the same exact direction, unless, what could I do that would change the direction? What do you think? We haven't talked about it yet. Yes, very good. What's going to happen if I make it negative? That's exactly right. So if I did this is like -2u, where the direction is just now the opposite way it was going before. It's now just petering off the other direction. Yep. Sure. Does that feel okay graphically what the scalar multiplication is doing? It's literally just scaling the vector, right? You guys maybe have heard of scale models. right? Like a Matchbox car is like a 1/12 or something of an actual car. I forget what it is. Maybe it's 1/64 or something. I don't remember. But it's like a scale model of actual vehicles. Or if you're looking at architectural plans, those are often scale models of the actual building, right? Probably do this in art class, I suspect. At some point, you do some scaling of an actual drawing, right, where you grid the whole thing out and then like reduce down the size of the picture to some smaller version or some bigger version. Yeah, is that a thing?
Yeah.
Okay, cool. Yes. All right. Let's do some numeric example here. Sound good? All right. So we're given a vector u, -2, 4, and a vector v, 7, 3, and asked to find the following vectors: u plus 2v, 4v, and then 5v plus -3u. So what I do to start is I'm going to start by just rewriting it with the component form vectors in their place. And then I'm going to follow the order of operations. So multiplication should come before addition. So I'm going to do that scalar multiplication first. Everybody's okay with how I did that? And now I can do my vector addition. So -2 plus 14 is 12. And then 4 plus 6 is 10. So again, following the theme that we've started off, the problem looks kind of complicated and a little bit scary, but what we actually end up doing, if you see what's going on, you understand what's going on, is really simple, right? The actual computation, what we're doing is we're just like multiplying and adding and subtracting whole numbers. Like, that sounds like elementary school math, Mr. Kulik. You know, like, kind of what the beginning start looks like a lot of the times. So if I have 4 times v, I'll start by doing the same thing. I'll just replace the vector v with its component form. And then I'll do 4 times 7 and 4 times 3. And that's all she wrote. Everybody's good there? The next one, notice here that we've written this as plus a negative, not subtraction. Why do you suppose we've written that as like 5v plus a -3u rather than 5v minus 3u? Have we defined what vector subtraction is? No, that's why, because we haven't defined vector subtraction. We will later, but because we haven't done it yet, I've written it as plus a negative to make sure that we don't be like, how do I subtract 2 vectors? You haven't told me yet. So that's the only reason why it's written that way. So again, I'll start by just dropping in my u's and v's. I'll follow my order of operations, so I want to do my scalar multiplications first. So 5 times 7 is 35. 5 times 3 is 15. -3 times -2 is +6. And -3 times +4 is -12. and then I can just add the components. So the x components, 35 plus 6 is 41. And if I add the y components, 15 plus negative 12 is 3. And we're done. Hopefully that feels pretty easy once you see, like, okay, it's just like adding and subtracting and multiplying whole numbers. It follows the order of operation just like before. I just have to remember that I only add x's, I only add y's. But otherwise, piece of cake. Okay. Next up, we're going to start worrying about defining vector subtraction. So we're going to start by defining instead the additive inverse. So like if we go back to the real numbers, if I talk about like the number 2, the additive inverse for the number 2 is the number when I add it to 2, I get 0. So negative 2. Unsurprisingly, the additive inverse of vector u is negative vector u, or negative 1 times vector u. Oh my gosh. So surprised. No, we should not be surprised by this. This should be, like fairly obvious definition. We want it to work just like the number system works. So we'll define things that way whenever possible. Now that we've defined the additive inverse, we can define what we mean by vector subtraction. So if we have, again, the vectors u and v, the difference between vector u and vector v is the same thing as plus the additive inverse. So u minus v is the same thing as u plus the additive inverse of v. Or really what it boils down to is just I subtract the components, which is what we would hope. Absolutely. Right? So if I subtract 2 vectors, I just subtract their components. If I add 2 vectors, I add their components. Works just the way we would hope it would. It's working just like regular number operations. Just go component by component. No big deal. And we mentioned already that multiplication of by negative 1 changes the direction, right? So we basically just add 180 or subtract 180 depending on, which way we're going. If we have a positive vector, we're adding 180. Or if our angle is less than 180, we're adding 180. If it's greater than 180, we'd be subtracting. We multiply by the negative. That's how the directional change. But that's the only scalar that changes direction is a negative 1, right? Another special kind of vector is called the unit vector. So in mathematics, when we talk about units, we're talking about something that has length 1. So a unit vector is just some vector whose magnitude is 1. If we think back to trigonometry, if you recall, we defined sine and cosine and tangent and all the other trig functions with respect to the unit circle. The radius on the unit circle is 1. So guess what the form of any unit vector is going to be? Well, any unit vector is going to be the form cosine theta, comma sine theta, right? Because those are the points on the unit circle. So if I go from the origin to any point on the unit circle, that's a radius that has length 1. Every unit vector is going to be of the form cosine theta comma sine theta. Is everybody okay with that idea? Just trying to connect what we're doing now back to what we did in first semester to try to reinforce some of these big ideas and show how, like, although this looks like the language here is different and the symbols are different, we're really doing the same thing, right? Josh? Sure. Yeah. So what we'll often be asked to do is to take some vector and rewrite it as a scalar times a unit vector. Or to find the vector that's the unit vector that's the same direction as a vector. So let's take a look at kind of how we might do that. So if we have some vector v, we can find the unit vector in the same direction as vector v by taking 1 over the magnitude of v and multiplying it by vector v. Yes. So if I want to find a unit vector in the same direction as vector v, that's what this formula does. Yes, we'll do a numeric example next to help you show you kind of how we're doing this. Because it looks a little weird, but when we actually do it, it's really straightforward. And it's like, oh, okay, that makes a lot of sense. So let's do a numeric example, right? This seems a little abstract right now, but if we do the numeric example and then we like kind of graphically show what's going on, it should make a whole bunch of sense. So here we're asked to find the unit vector in the same direction as the vector 5, comma, -6. So the first thing I'm going to do is calculate the magnitude. So that's the x component squared plus the y component squared, all square rooted. So 25 plus 36 is 61. So that's the square root of 61. So my unit vector then should be 1 over the square root of 61 times my vector v. So if I go and I do that scalar multiplication, I get that, right? If I multiply 1 over square root 61 by 5, I just get 5 over 1 times 1 over square root 61 to give me 5 over square root 61. Similar with when I multiply it by 6. And we probably don't leave our answer like that. What do we not like about this answer? Square root in the denominator. So we'll rationalize those denominators. So that's our answer. Notice that if I look at the magnitude of this vector. Oops. What do I expect to get here? 1, because it should be a unit vector now. So that's what we've done. Colby.
When you're finding a vector with anything, do you always use a square formula?
You said something at the end and I kind of mumbled. I didn't catch what you said.
Square formula, like.
So that is the formula to find the magnitude of a vector.
Oh.
Is all I did there. So if we think about graphically what we just did, say here's our, well, I guess it was down here. Say this is our vector v, right? 5, -6. The length of this vector is that, right? If I multiply this vector by 1 over its length, it'll scale that vector so that it just has length 1, right? If I take 1 over its length and multiply it by that vector, well, the vector should now just have length 1. That's graphically what this is doing, right? If my vector has length 2 and I scale it by 1/2, the vector now has length 1. That's all we're doing with that formula. Does that feel okay? Hopefully, visually, that helps kind of connect what this formula is actually doing. It's like, oh, yeah, okay.
So it goes from the red to the green, or the green to the red?
So I'm just kind of showing you kind of what U and V look like. I'm just showing you kind of what U and V look like, what this process is really doing, right? If I take that vector V and I multiply it by 1 over its length, it turns into the same vector. It's going in the same direction. It just has length of 1 now, right? It's now turned into a unit vector. Okay, so as you might have guessed, these unit vectors are kind of important. And of all the possible unit vectors, remember, all the points on the unit circle correspond to a unit vector. There are 2 that we have a special name for. We call these 2 vectors the standard unit vectors. We give one of them the name I. That's the vector I. So that's like wearing the vector hat, which is just the vector 1, 0, and the vector j, which is the vector 0, 1. And why we've done this is this allows us now a way to take any vector in component form, and I can rewrite this now as a vector in, or as the sum or difference of standard unit vectors. So if I have the vector in component form CD, I can break that up into two vectors, the vector C comma 0 and the vector D, or 0 comma D, right? If I add those two together, I just get CD again. And I can pull a scalar off of C comma 0 and just have that C times 1, 0. And similarly with 0D, I can pull the scalar D off and make that D times 0, 1. And this is just my unit vector I, and this is just my unit vector J. So it allows me to take a component form vector and translate it into a sum of unit vectors. Or difference, depending on whether the C's and D's are positive or negative. We call this form, where I have my vector written as the sum or difference of unit vectors, this has a name. We call this linear combination form. Okay, so there's just another way to represent a vector. So we have the vector could be represented as 2 points, its head and tail, component form with the wedged brackets, with a magnitude and direction, or now a fourth way as a linear combination form. So using these standard unit vectors. So it's just a fourth way now of representing these vectors. The reason that we end up with all of these different representations is depending on the context. It's easier to deal with the problem in some of these different forms. It just makes life easier. So we have different ways of writing this. Just like fractions and decimals are appropriate. See, it makes the problem easier one way versus another. They're both representing the same number. But depending on the problem, you might want one way versus the other. Might make it life easier for you. Okay. Next up, we have another vector operation to define now. This is called the dot product and the dot product is a little unusual because what we do is we're going to take two vectors and we do the dot product of them. What we get back is a scalar. So the input is two vectors and the output is a number, not a vector. The way we perform this dot product is we take the product of the x coordinates, or I should say the x components, plus the product of the y components. That's the formula. The product of the x's plus the product of the y's. That number is our dot product. It is a number, not a vector. So a couple basic properties of dot products. are as follows. So the dot product is commutative. That means that u dot v is the same as v dot u. The multiplicative identity property says the dot product of the 0 vector with any other vector is just the number 0. So keep in mind that's the number 0, right? The other one is the vector 0. The dot product is distributive. So u dot v plus w is the same as u dot v plus u dot w. And it doesn't matter if you do the sum, if the sum is first or second. The fourth property is called the scalar associative property. So if I have a scalar times a vector, dot product with another vector, it doesn't matter when I do the scalar multiplication. I could do the scalar multiplication with the first vector and then do the dot product. I could do the scalar multiplication with the second vector and then do the dot product. Or I could do the dot product and then do the scalar multiplication. It doesn't matter when that happens. And the last one is that the dot product of a vector with itself is just the same as the magnitude of that vector squared. So if you think about it, the dot product of u with u is going to be u1 squared plus u2 squared, which is the same thing as u1 squared plus u2 squared, all square rooted and then squared, which is the magnitude squared. All right, let's do some numeric example using these dot product and dot product properties. All right. So it says, given that u is the vector 2, -3, v is the vector -1, 5, w is the vector 8i plus 4j, use the definitions of dot products and the above properties to solve the following problems. Before I would start on this, what's weird about the way my vectors are given to me? Yeah, so great. Vector w is not written in component form, right? It's in that linear combination form. How is my formula for dot product given? It's for vectors in component form. So the first thing I'm going to want to do is to rewrite vector w as a vector in component form. Well, that's really easy. The I coefficient is my x component, and the j coefficient is my y component. I'm done. No biggie. So if I do u dot v, I'm going to start by just recopying the vectors here. And my formula for dot product is the product of the x components plus the product of the y components. So my result is the number -17. So far, so good. Okay. The next one is w dot v. I'm going to do that the same way. So I'll recopy down my vectors for w and for v. My formula for dot product is the product of the x components plus the product of the y components. So the result is just the number 14. Again, the computation here is really simple, right? Do I just have to remember the formula and understand like what it is that I'm doing? Sure. But like the actual nuts and bolts of what it is that, like how to do this, the how is so very easy, right? Like what to do and when to do it, that's the tricky part for this chapter. The actual hows are very easy. All right, the next one is 5w.u. So this one, I'm going to actually use, what I like to do is I like to use the scalar associative property to say this. So what I'm going to do is I'm actually going to do 5 times the dot product of u and w, or w and u. So I like to do the dot product first and then multiply it by 5. But you could have done the multiplying 5 to either vector first and then do the dot product. That is fine. Colby.
Do you know which formulas you're going to use? Like, if you scroll up.
It doesn't matter which version, which part you use. You could multiply the 5 to vector, hold on a second. I got to look at the problem again. 5 to vector w. You could do the 5 times vector w first and then do the dot product. Or you could multiply the 5 to vector u and then do the dot product. Or you could do what I did and do the dot product and then multiply by 5.
Oh, how do you know if you're going to use like cumulative property?
Because of what it looked like. When I looked at the problem, I had C U times V, right? So just based on what it looked like in the beginning. Is that what you, okay. Sorry, I misunderstood what you're asking.
And what did you write next to the multiplicative identity? It's just like plus number.
Oh, that's pointing out that this is the number 0, not the vector 0. Because I'm using that bold face in typing. Sometimes it's hard from the people sitting in the back to tell the 0 is bolded or regular typeface. So I wanted to just make sure that I pointed out that the 0 vector is one of them and the 0 number is the other. That's all I was trying to say there. And the last one is D. So that was U minus W dot to V. Okay, so I'll start by just rewriting these. Now, what do I need to do first here? Yeah, I would definitely do that. So that's negative 2 minus 8 is negative 6. And then negative 3 minus 4 is negative 7. So I would probably do, I mean, that's fine to do it that way, Max, absolutely. I would do this just because it makes the arithmetic keeps the arithmetic small. But you could certainly do what you just said. That's not incorrect. But I like to do the dot product before I do the scalar multiplication. But it doesn't matter. Oops, that's not right. Look what I did. Forgot a negative sign. Eep. That's negative 29. So I have negative 58. Sorry about that. That happens every once in a while, right? We drop some negative sign. Ah! All right. We have one more set of ideas and we're done for today. So the next thing I want to talk about is how to find the angle between two vectors. So the angle between vectors u and v is going to be cosine inverse of the dot product of vectors u and v divided by the magnitude of u times the magnitude of v. Most of the time we'd just be using this version. I'm not going to prove this for this class. It's basically using the law of cosines, though, is essentially all you're doing. But it's beyond the scope of what you guys need to worry about, so we're just not going to worry about it. We're going to just skip straight to using it with a numeric example. Is that okay with you guys? Yes. Oh, that got big. So here we're asked to find that measure of the angle between vector u and vector v. What I would suggest to you to start, especially as the first few times you're doing this to help build some intuition, is I'm going to draw a picture of what this two vectors look like and what the angle is that we're looking for. So I can get a good idea is the answer I'm getting reasonable or not? So here's my axis. So my vector u is like 7 over and 6 down. And then my vector v is 2 over and 2 up. So if I'm just kind of eyeballing that, to me it looks like that angle is around 90 degrees. Everybody agree? So if I'm getting something like between 80 and 100, I'd feel pretty good about what I did there. And the more careful you are about like making tick marks and counting, the better estimate you can get out of that just from a get-go. Everybody's okay? Okay, so to do this, I need to calculate three things. I need U dot V. And now my pen's being stupid. So I'm getting all these extra little messy marks. I don't know what it's doing. But it's really making me angry. Hold on a second, guys. I'm just going to do this real quick and see if that fixes it. Ooh, that got big. Nope, it didn't. All right, well, I apologize for now. So I get 2 for the dot product. Then I'm going to need the magnitude of U. So 49 plus 36 is 85. And I need the magnitude of V. So 4 plus 4 is 8. So my answer is going to be the cosine inverse of 2 divided by square root 85 times square root 8. So I'll go to my calculator, do cosine inverse, and then use my fraction command, 2 over square root 85 times square root 8. Notice that I did not even think once about trying to simplify any of these radicals or rationalize the denominator or anything like that, because this is not a final answer. I don't care what any of those values are. They don't have to be simplified or made nice. It's all just going into my calculator anyway. I get 85.60, which is squarely in the range of values that I would have expected. So I feel pretty doggone good about that. What do you guys think?
Is it like 85,260?
That's 85.60. Yeah. That's what I got there. All right. One final definition. There's one special kind of pair of angle or pair of vectors. So we say that 2 vectors are orthogonal if the angle between them is 90 degrees. And the easiest way to check for that is just if their dot product is 0. So orthogonal just means that the angle between those 2 vectors is 90 degrees. So if you're asked to show if 2 vectors are orthogonal, you could do that process that we just did above to show that their angle, that the angle between them is 90 degrees, or you can just check their dot product. So -5 times 16 is -80, and positive 8 times 10 is positive 80, and those add to give me 0, so I know they're orthogonal. That wraps us up for today. So you guys should be able to do 15 through 40 at this point. As a reminder, your problem set due Sunday is just 1 through 14. So you just add that to the homework tab on your OneNote. 15 through 40 will be due the following Sunday at midnight, along with whatever else we assign in the interim. I believe that the first 2 sections is what the homework quiz will be based on. So you should probably expect to see a homework quiz at some point next week. So you should be able to convert between the different forms of vectors and do vector operations, and should be good. If you can do that stuff, you should have no problem on the homework quiz. We'll also have a Delta Math coming up this week that'll probably get packaged on the same day as the homework quiz. Those are usually a good combination where you can just like finish the homework quiz and roll right into the Delta Math. Yeah, that's about it. Everything going okay, guys? Okay, very good.